Ever wondered how your credit card company detects fraudulent transactions among millions of normal ones? Or how a network security system identifies unusual traffic patterns indicating a potential cyber attack? These instances are not mere coincidences, but the result of a complex process known as anomaly detection. This technique is not just limited to these examples, it plays a crucial role in various fields, from healthcare to industrial monitoring and even in social media management. Anomaly detection is an intriguing aspect of machine learning, a field that combines statistics, artificial intelligence, and data analysis to find patterns in data. It's like a digital detective, tirelessly sifting through mountains of data to find those precious few outliers that could signify a major issue or opportunity. These are not random guesses, but calculated detections brought about by none other than anomaly detection in machine learning. To understand anomaly detection, imagine yourself in a room full of people wearing red hats, and suddenly someone walks in with a green hat. Now let's break this down. The room represents a dataset, a collection of information where each piece of data is like a person in that room. The red hats symbolize the commonality within that data, the patterns and regularities that we come to expect. Then someone walks in with a green hat. This individual stands out, doesn't fit the pattern, and catches our attention. This, my friends, is an anomaly. In data science, anomaly detection is a bit like being a detective. You're looking for the unusual, the unexpected, the outliers that deviate from the norm. These anomalies can be a result of an error, but they can also indicate an important and perhaps a groundbreaking discovery. For instance, in a dataset of credit card transactions, an anomaly might be a sudden large purchase in a foreign country. This could indicate fraudulent activity, or in a medical context, an anomaly in a patient's test results could signal a health issue that needs immediate attention. The challenge here is that anomalies are rare by definition. They're needles in the proverbial haystack. And this makes them tricky to find. It's not as simple as just spotting the person in the green hat. Often the anomalies are subtle, hidden in the complexities of large and diverse datasets. But with the power of machine learning, we can train models to detect these anomalies. These models learn from the data, understanding what's normal so they can spot what's not. They can sift through vast amounts of information, picking out the anomalies with remarkable accuracy. In essence, anomaly detection is about finding the unexpected, the deviations from the norm that could signal something significant. It's about finding the green hats amongst the red. In the world of machine learning, the person wearing the green hat is the anomaly that the algorithm detects. So, how does machine learning come into play in anomaly detection? Let's dive in and discover the fascinating relationship between these two. Machine learning, in essence, is all about learning and predicting from patterns. It's a tool that teaches computers to do what comes naturally to humans, learn from experience. In the context of anomaly detection, machine learning algorithms are trained to understand what's normal, what's typical. And once they've absorbed this normalcy, they can then effortlessly spot the anomalies, the outliers, the unexpected. Think of it as a sentinel standing guard, ever vigilant. It knows the day-to-day, the routine, and when something abnormal occurs, it raises an alarm. That is what machine learning does in anomaly detection. From credit card fraud to network security, machine learning algorithms are the unsung heroes identifying potential threats and risks, allowing us to take timely action. But how does an algorithm learn what's normal and what's not? The answer lies in the training data. This is a dataset that represents typical behavior, and the machine learning algorithm studies this data to understand the patterns and relationships inherent within. It's like giving a detective the background information on a case. The more comprehensive and representative the training data, the better the algorithm will be at distinguishing anomalies. However, it's not just about having a large quantity of data, but also the quality of data matters. The algorithm needs clean, well-prepared data to learn effectively. Garbage in, garbage out, as they say in data science circles. So the process of preparing and curating this training data is as critical as the algorithm itself. While machine learning makes anomaly detection more efficient and precise, it's not a magic wand. It needs the right data, the right algorithms, and the right tuning to do its job effectively. But when all these pieces fall into place, it's a powerful tool that can help us identify risks and prevent potential issues before they escalate. Like a detective, the machine learning algorithm uses patterns and evidence from data to spot the anomalies. Just as Sherlock Holmes uses his keen observation and deduction skills, machine learning uses data and algorithms to solve the mystery of anomalies. Different problems require different solutions, and anomaly detection is no exception. In the vast landscape of anomaly detection, there are several key techniques that stand out. These techniques, each with its unique strengths and applications, are the tools we use to identify the odd ones out in our data. Today we'll delve into some of these techniques, namely statistical methods, clustering, classification, and neural networks. Statistical methods are the old stalwarts of anomaly detection. They've been around for a long time and they're still quite effective. These methods rely on the premise that normal behavior can be modeled by statistical distributions, and anything that deviates significantly from this model is an anomaly. For instance, if a data point is located 3 standard deviations away from the mean, it's considered an anomaly. Simple, yet effective. Next up, we have clustering methods. Clustering is all about grouping similar things together. In the context of anomaly detection, we cluster the data points and then identify the points that don't belong to any cluster or belong to small and sparse clusters as anomalies. The famous k-means clustering algorithm, for example, partitions the data into k-clusters, and the data points far away from the centroids of these clusters are considered outliers. Then we have classification methods. In these methods, we use a training dataset to teach our model what normal and anomalous data look like. Once the model is trained, it can classify new data as either normal or anomalous. For example, the support vector machine, or SVM, is a popular classification method used in anomaly detection. SVMs define a boundary around normal data, and any point that falls outside this boundary is considered an anomaly. Last but not least, we have neural networks. These are a type of machine learning model that mimic the human brain's own network of neurons. They're particularly good at detecting anomalies in large and complex datasets. One type of neural network used in anomaly detection is the autoencoder. It's a network that's trained to reconstruct its input data. When it comes across a data point it can't reconstruct well, it flags that point as an anomaly. Each of these techniques has its own strengths and weaknesses, and the choice of technique depends on the specific problem at hand. Statistical methods are simple and efficient, but they may not perform well with complex data. Clustering can be effective with unlabeled data, but it might struggle with high-dimensional data. Classification requires labeled data, which can be hard to come by, but it can handle complex patterns. And neural networks can deal with large and complex datasets, but they require a lot of computational resources. Choosing the right technique is like choosing the right tool for a job. It can make all the difference in effective anomaly detection. So where does anomaly detection fit into our daily lives? You might be surprised to learn that it's all around us, quietly working in the background to keep us safe, efficient, and informed. Consider credit card transactions. Every time you use your card, sophisticated algorithms are running in the background, analyzing the transaction for anything unusual or out of place. If an anomaly is detected, such as a purchase in a location you've never been to before, the system flags it as potential fraud, protecting your finances. Similarly, in the world of network security, anomaly detection plays a crucial role. Unusual patterns of network traffic could indicate a cyber attack or data breach. By identifying these anomalies, security systems can respond swiftly, minimizing damage and protecting sensitive information. In healthcare, anomaly detection is used to identify rare diseases or conditions in large patient datasets. It can even be used to detect unexpected changes in a patient's health data over time, which could be an early warning sign of a health issue. While these applications are incredibly beneficial, they are not without their challenges. One of the key challenges in anomaly detection is dealing with high-dimensional data. Because anomalies are often subtle and hidden in a sea of normal data, trying to identify them in large, complex datasets can be like finding a needle in a haystack. Another challenge lies in the balance between false positives and negatives. If the system is too sensitive, it may flag normal data as anomalies, leading to false positives. On the other hand, if it's not sensitive enough, it may miss actual anomalies, leading to false negatives. Striking the right balance is crucial yet challenging. Despite these challenges, the power of anomaly detection in making sense of vast amounts of data cannot be overstated. It's a critical tool in our data-driven world, helping us to make sense of the incomprehensible and keep a step ahead in an increasingly complex world. Despite its challenges, the power of anomaly detection in making sense of vast amounts of data cannot be overstated. Let's take a moment to soak in what we've unraveled about anomaly detection. We've delved into the heart of this fascinating field, exploring its essence as a quest to identify outliers or irregularities in data patterns. We've discovered a variety of techniques, each with its own strengths and quirks. From statistical-based methods to clustering and classification techniques and the more complex deep learning approaches, we've seen how these tools are applied to uncover the unexpected. We've also peered into its applications, understanding how anomaly detection is leveraged in numerous sectors, from healthcare and finance to cybersecurity and industrial processes. Yet we've also acknowledged its challenges, the difficulties of defining what an anomaly is, the risk of false positives, and the need for high-quality data. Remember, in a world overwhelming with data, anomaly detection serves as a lighthouse, guiding us to the insights that truly matter.